So in this video, we're going to be looking at buffers and their calculations as well, right? Now, starting off, we've got a buffer, and a buffer is just a solution that minimizes any changes in pH when small amounts of either acid or alkali is actually added. Now, this doesn't work if you add in large amounts of acid or alkali, and the buffer solution is actually designed to actually withstand any changes in pH itself. Now, let's say if we were to look at a buffer solution itself, it has to consist of the following three. It needs to have a high concentration of weak acid, and that could be anything like an organic acid, like let's say glycolic acid, ethanoic acid, and so on. We need to have a high concentration of conjugate base, which could be the conjugate base formed from these acids. So glycolic acid forms glycolic ions, ethanoic acid forms ethanoic ions, propanoic acid forms propanoic ions, and we also need to have a very low concentration of H plus ions itself. Now, our buffer solution, we need to be able to memorize that it works best when the pH of the buffer solution is equal to the value of pKa, and this happens when the concentration of HA, our acid itself, is equal to the concentration of A minus, our conjugate base within the buffer. Now let's look at how a buffer actually works, right? I've got an equation here, a buffer equation to show a ethanoic acid buffer, where I've taken ethanoic acid and I've formed ethanoic ions and H plus ions itself. Now you can see I've got a very high concentration of ethanoic acid, my HA, and I've got a very high concentration of my ethanoic ions, my A minus itself. The H plus concentration is also going to be very low. Now there's two scenarios that you need to be able to explain when it comes to the exam on how a buffer actually works. And let's say if we were to start off by adding some acid, let's say if I were to add in very small amounts of HCl, right? HCl, that's going to dissociate and that's going to form H plus ions, and then it's also going to form chloride ions as well. Now the H plus ions in this case itself is going to go ahead and it's going to react with this very large amount of conjugate base that we can see over here. And what that will actually do is that will shift the position of the equilibrium towards the left, and so in doing so we actually make more of ethanoic acid. And so if we've now added H plus itself into our buffer solution, the buffer solution will get rid of any extra H plus by shifting the equilibrium to the left to make more undissociated acid itself. So yeah, we need to make a final statement in this as well, where we say that any change in pH is minimized as well, right? What about if we were to add an alkali? Let's say if we were to add in, let's say, sodium hydroxide, which we know dissociates to form sodium ions and, more importantly, hydroxide ions as well. Or let's say if we were to take ammonia, right, which is a weak base that reacts with water, and what that actually forms is ammonium ions, which isn't really the important one, but the more important actual thing that comes from this is the hydroxide ions. Let's say these hydroxide ions were added to our buffer solution. What would happen is that the OH minus ions would react with our acid, in this case, our weak acid, which is going to be ethanoic acid. That would shift the equilibrium towards the right. And so, right, what actually happens is we make more H plus, we counteract the change in pH, and so we can say that any change in pH has been minimized as well. So we need these 3 points over here. So yeah, right, looking at how we can actually make a buffer solution, well, there's two different ways to make a buffer solution. The first method, which is very nice and easy, is where we add a salt of a weak acid. Let's say if I'm dealing with ethanoic acid, I would add the salt of ethanoic acid, let's say sodium ethanoate in this case, to an excess of a weak acid, such as, let's say, ethanoic acid itself, right? And what will actually happen is that we end up with a very high concentration of ethanoic acid, because that's what we've done here. We've taken a solution of excess weak acid and we've added to that, right, a salt of ethanoic acid, which is going to be sodium ethanoate. And we know when we add something like sodium ethanoate, which is going to look like this, CH3COONA, what will happen is that will actually dissociate, and it will dissociate completely to form ethanoic ions, which is what is very important. That's what we need. And then we will also form sodium ions as well. Now, if that forms, right, lots of these ethanoic ions, that means that we have a very high concentration of our conjugate base, right? So in that case, our salt, and so we now have a buffer solution. Now, what about if I were to look at method 2, right? In method 2, it's slightly more trickier here. Instead of actually taking the salt and putting it into a solution like we did over here, what we're actually doing is we're actually making the salt in solution itself. So yeah, let's say if we were to take a weak acid like ethanoic acid, and again, we were to put that in excess, right? What we would do this time is we would actually add in some sodium hydroxide, some sodium oxide, some sodium carbonate, or even sodium metal on its own. And what we can actually make is a high concentration of salt by doing that as well. So what we say is that the excess weak acid itself is going to be partially neutralized to make ethanoic ions, which is going to be our salt, with either a metal oxide, metal hydroxide, or a metal carbonate as well. But the key part here is that some acid actually remains. And so you can see, right, in our first equation over here, we end up with the partial neutralization of ethanoic acid reacting with sodium hydroxide, and we end up making our salt, right, our conjugate base, which is going to be sodium ethanoate, and then we make water as well. Now the important bit is that we've actually made our salt over here within the solution itself, and so that salt, just as we showed above over here, that salt itself is going to dissociate to form lots of this conjugate base itself. So we have lots of sodium ethanoate, so we have lots of ethanoic ions, and so, right, we end up with the same buffer equation again, with a high concentration of our weak acid and a high concentration of our conjugate base itself. So yeah, let's look at how we can actually explain that using a diagram. Well, you can see over here, right, I've got two different solutions. I've got solution 1, and then I've also got solution 2 over here, right? Now I've got the first solution, which is where our weak acid is going to partially dissociate. We know the equilibrium is going to lie well over to the left, and so we end up with a very large amount of ethanoic acid itself and a very small amount of conjugate base and acid itself. That's why we can't actually just use any weak acid on its own to make a buffer solution. We don't actually have enough conjugate base, and so let's say if I were to add any acid to this, which contains H+, the H+ would actually run out of conjugate base itself before any changes is actually minimized, right? Now let's say if I were to look at the second solution, we've got a salt and that completely dissociates, and so you can see sodium ethanoate, right? It's matching in terms of its ion itself. We've got ethanoic acid, ethanoic ions, and so we've got sodium ethanoate, and what happens is this actually completely dissociates, and what we end up with is a very large reservoir of ethanoic ions itself and then sodium ions itself, which isn't really that important. Now if that's the case, we know we've got a large reservoir now of ethanoic acid, and then we have a very large reservoir of conjugate base A-, which in this case is going to be ethanoic ions itself. So in that case, we now have formed a buffer solution by mixing both of our two solutions of a weak acid and a salt together as well. Now, if you were to look at method 2 buffers, because this was just method 1, right, you end up forming the same kind of product over here, the same solution over here with the same reservoirs, but the only thing is that you actually make your salt within the actual beaker itself, or the reaction mixture, or the buffer solution itself, right? So yeah, moving on, right, let's look at actually calculating the pH of a buffer solution. Well, this is actually pretty straightforward, right? When you calculate the pH of a buffer solution, you normally need to find a bunch of different things. Now, in this case, it's very different to when you're dealing with weak acids. Yes, you do use the K expression, as you can see over here, that we've got rearranged to find the concentration of H+, but in this case, you're finding the concentration of H+ for your buffer, and so you can use that to actually work out a value for pH of your buffer as well. Now, sometimes you could be asked to work backwards, but again, it's just simple algebra and rearranging equations to get the right subject and then calculate the right value itself as well. Now, when we look at the concentration of H+, right, we've already said that this does not equal the concentration of A-, right? That doesn't actually happen. And so when we look at the actual salt itself being added, we know that because we add in more salt, let's say in our previous example, we added in sodium ethanoate. If I were to add in more ethanoic ions, that actually means that we end up with a larger concentration of our salt, which in this case is going to be A- compared to H+ itself. So again, right, the assumption that we made for weak acids, where we said Ka is equal to the concentration of H+ squared divided by the concentration of HA, right, that no longer works because the concentration of H+ no longer equals the concentration of A- itself. We've added in extra A-, extra salt into our solution itself, right? So yeah, if that's the case, right, this equation to calculate the H+, the concentration of H+ within our buffer, we can rearrange it to get the following, where we can calculate a value for Ka. We can also calculate a value for the concentration of the acid that we actually need, as well as the concentration of the actual conjugate base, the ethanoic ions, for an example, that we actually need as well. Now, exam questions, right, we don't actually use the terms concentration of HA or concentrations of A minus. We always use the actual formula used itself. So let's say if I were to find the concentration of H plus for my buffer, I know that's going to be equal to, right, Ka times by the concentration of, let's say, for example, ethanoic acid, which is going to be CH3COOH, divided by the concentration of my conjugate base, which is going to be CH3, and then it's going to be COO minus in that case, right? We need to lay it out in this format as well. So yeah, let's look at an example together. We're asked to calculate the pH of a buffer solution made by mixing 14 centimeters cubed of 2 mole per decimeter cube ethanoic acid. That's got a Ka as given here, and we're told that's mixed with 15 centimeters cubed of 1.5 mole per decimeter cubed of sodium ethanoate itself. Now the first thing is we actually need to find the number of moles of both ethanoic acid and our sodium ethanoate itself. And so let's say if I were to work out my number of moles, I can then put that into my formula. I can find concentration. I can put that into my formula to calculate Ka, rearrange that to calculate the concentration of H plus because I've been given Ka, and then I can work out pH itself as well. So yeah, let's say if I were to start off by calculating the concentration of ethanoic acid, I'm going to do the number of moles is equal to the concentration times by volume, which is going to be equal to 2 times by 14 over 1,000 itself as well. And that's going to give me an answer, which is going to be equal to 0.0280, and that's going to be moles itself, right? Now I can find the number of moles of my actual conjugate base, which in this case is going to be sodium ethanoate, CH3COO, and that's going to be the same as the concentration of my conjugate base, which is going to be CH3COO minus, because remember, you're dealing with a salt here, and that salt itself of sodium ethanoate is going to completely dissociate to form sodium ions, and it's also going to form ethanoate ions itself. So you've got CH3COO minus. Look at the molar ratios. You've got a 1-to-1 molar ratio. So for every mole of sodium ethanoate you have 1 mole of ethanoate ions itself as well. That's the relationship that you need to be able to make, right? So yeah, if you ever hear the word salt, you know that you're talking about this substance over here. If you ever hear the word conjugate base, you also know that you're talking about this substance over here as well. So continuing with the rest of this calculation, I'm going to do concentration times by volume, which is going to be 1.5 times by 15 over 1,000. And so what I end up with is a value of 0.0225 moles itself. So I've got two values for the number of moles. Now I could work out the concentration for the overall solution itself, and to do that, right, I would need to take 14 and add that to 15, because our new buffer solution is going to have a new volume, and that new volume is going to be 29 centimeters cubed itself, right? But I don't need to do that. The reason why is because when we actually deal with our expression to calculate the concentration of H plus itself, so let's say if I were to find the concentration of H plus of my buffer, right, I know that that's going to be equal to a value of Ka times by the concentration of ethanoic acid divided by the concentration of my conjugate base, which is going to be ethanoate ions itself as well. Now, if we were to look at this, right, we do call this salt sometimes as well, this ethanoate ion salt sometimes as well, as we mentioned before. If we were to look at this, right, if I were to divide by the same volume at the top and at the bottom, right, the volumes terms will actually cancel, and so what I actually end up doing is just putting the numbers of moles in, and this is the only time where this actually works here itself. And so if I were to do that, right, I know that I'm going to do the Ka value, which is going to be 1.76 times 10 to the power of minus 5 in brackets, right, times by the concentration of my acid, which in this case is going to be 0.0280 moles, and I'm going to divide by the concentration of my conjugate base, my salt, my ethanoate ions, which in this case is going to be 0.0225 moles itself, right? Again, we could have just worked out the concentration overall for each one of these out of 29 centimeters cubed, but I don't have to, because then volume terms are going to cancel at the top, at the bottom. That means that they can cancel. I do that, and what I actually end up with is a value for the concentration of H plus as being 2.19 times 10 to the power of minus 5, and that's going to be in mole per decimeter cubed. I can then calculate a value for the pH, which is going to be equal to minus log to the base 10 of the concentration of H plus, which is going to be 2.19 times 10 to the power of minus 5 itself. I put that in my calculator, and what I end up with as a value for pH is going to be 4.66 to 2 decimal places as well. Right, so you get quite a few different marks over here, and again, right, this is how you calculate the pH of a buffer itself. Now I want you to have a go at the following example over here. Pause the video and resume once you're ready to move on. So yeah, in this question we're asked to calculate the pH of a buffer solution made by mixing 50 centimeters cubed of 0.3 mole per decimeter cubed ethanoic acid, which has a Ka value of 1.76 times 10 to the power minus 5, and 100 centimeters cubed of 0.6 mole per decimeter cubed sodium ethanoate. So straight away we know over here we've got a method 1 buffer, and so we don't actually need to do any extra steps. We just follow our calculation out as normal, work out the moles, find the concentration if needed, right, but our volume terms cancel, remember, find the concentration of H plus, and then actually calculate a value for pH itself, right? So again, to work out the number of moles of ethanoic acid in this case, right, same acid as before, we're going to do concentration times by volume, which is going to be 0.3 times by 50 over 1,000 because we need it in decimeters cubed, and what we end up with is a value of 0.0150, and that's going to be moles itself. Then I can find the number of moles of ethanoic ions, right? So in that case, remember, we're dealing with our salt here, our conjugate base that fully dissociates, forms ethanoic ions, and what we end up with is concentration times by volume, which is going to be equal to 0.6 times by 100 over 1,000, and what we end up with for a value for our concentration of our A minus is going to be 0.06 moles itself, right? So I've got 0.06 moles. So the next thing I can do is actually work out a value of the concentration of H plus, and that's going to equal Ka times by the concentration of ethanoic acid, and so that's going to be divided by the concentration of A minus, our salt, our conjugate base, whatever you want to call it. And so if I plug in some numbers, I end up with 1.76 times 10 to the power of minus 5, and then that's going to be times by our concentration, which is also going to be the same as our moles in this case because it doesn't really matter. Again, the volume terms cancel, and so our acid is going to be 0.0150, and then that's going to be divided by 0.06 itself, right? Now I plug that in my calculator and I end up with the value of 4.4 times 10 to the power of minus 6 itself, and that's going to be in mole per decimeter cubed. And then, right, what I can do is find pH, which is going to be equal to minus log to the base 10 concentration of H plus, which is 4.4 times 10 to the power of minus 6, and then I end up with a value that's going to be 5.36 itself for my pH. So yeah, moving on, right, we could also be asked to find the ratio of acid to salt or salt to acid within the buffer itself. So to do that, right, let's say if I were to take my expression again for Ka, that's going to be equal to the concentration of H plus, and then that's going to be times by the concentration of A minus. I'm just using the general acid in this case, and then I'm going to divide that by the concentration of my acid, and so I can actually rearrange this equation over here to give me the ratio of my acid to salt, which is what I've got over here, and then it could also give me the ratio of my salt to acid itself as well. Remember, this A minus is going to be your conjugate base or your salt, right? And so let's say if we were asked to calculate this ratio, we can use both of these two equations to work out the actual ratio of acid to salt or salt to acid itself as well. So moving on, right, feel free to have a go at the following example, pause the video and resume once you're ready to move on. So yeah, we're asked to calculate the pH of a buffer solution made by dissolving 34.7 grams of butanoic acid with that value of pKa, and we're told that we've got 12.8 grams of sodium butanoate in water, making up the volume to 250 centimeters cubed itself as well. So in this case, right, we're dealing with masses, so we can find the number of moles by doing N is equal to M over MR. Again, right, we've got a method 1 buffer over here because we're not dealing with any bases that's going to react with the excess weak acid, and we're also calculating the ratio of acid to salt and the ratio of salt to acid as well. So let's say if I were to work out the number of moles of butanoic acid as well, we need to be very specific about what we put over here. So if I've got butanoic acid over here, right, the number of moles of that is going to equal the mass over the MR itself, which is going to be equal to 34.7 divided by the mass of butanoic acid, which is going to be 88. and then I'm going to end up with a value that's going to be 0.394 itself in terms of the number of moles. And then let's say if I were to work out the number of moles of my salt, my A minus, sodium butanoate, which is going to be looking like this. I'm not going to write the formula out just because of time. And I'm going to do the same thing again, the mass divided by MR, which is going to be equal to the mass in this case, which is going to be 12.8 grams itself, and we're going to divide that by the MR, which is going to be equal to 110, right? Now remember, when we're working out MR, we're actually looking at the MR of sodium butanoate, because that is our salt itself. That's what we've dissolved. We don't just look at butanoate on its own, we look at sodium butanoate. And so if that's the case, right, we can actually end up calculating a value which is going to be 0.116 moles itself, right? Now the next step is to actually find the concentration of my butanoic acid, and so to find the concentration of butanoic acid, right, which is going to be CH3 CH2 CH2 COOH, what I'm going to do is I'm going to take the number of moles and divide by the volume, and so I'm going to do, right, 0.394 divided by the volume, which is going to be 250 divided by 1,000. And what I end up with is a value for the concentration as being 1.57 itself, and that's going to be mole per decimeter cubed as well. I can do the same thing, find the concentration of sodium butanoate, which is going to be CH3 CH2 CH2 COONA. And to find the concentration, again, number of moles divided by the volume, and that's going to be equal to, in this case, right, 0.116 divided by the actual volume, which is going to be 250 over 1,000. And what that gives me a value of is going to be 0.4652. And so that's going to be 0.465 to 3 significant figures as well. So yeah, if I were to calculate the concentration of H+, that's going to be equal to Ka, and that's going to be times by the concentration of butanoic acid. So that's going to be CH3, CH2, CH2, and then it's going to be COOH. And then that's all going to be divided by the concentration of butanoic ions, which is going to be CH3, CH2, CH2, and then it's going to be COO minus itself, right? So I'll sub in my numbers. I'm going to have Ka, right, which in this case is actually not given to us. We're actually given pKa, but remember, you can calculate a value of Ka by doing 10 to the minus pKa, which is going to be equal to 10 to the minus, right, in this case 4.78. We put that in our calculator, and what we actually end up with is a value of 1.66 times 10 to the power of minus 5 itself, right? So yeah, that's going to be 1.66 times 10 to the power of minus 5, and that's going to be times in the concentration of our acid, which is 1.57, and we're going to divide by the concentration of our conjugate base, our salt, which is going to be 0.465 itself. I'll put that in my calculator, and I end up with the value of 5.60 times 10 to the power of minus 5, and again that's going to be mole per decimeter cubed itself, just like our other concentrations. So again, I need to find a value for pH, which is going to be minus the log of that, and so that's going to be the minus log of 5.6 times 10 to the power of minus 5. I put that in my calculator, and I end up with the value of 4.25 as my pH itself. So now this question doesn't actually finish over here, right? Because the next thing that I need to do is I need to actually find a value, right, for the ratio of acid to salt and salt to acid. And so, right, if I were to look at the concentration of the acid, which is CH3, CH2, CH2, and then it's going to be COOH, and then divide that by the actual concentration of the salt itself, which is CH3, CH2, CH2, COO minus, because it's the same as the conjugate base itself. I know that's going to be equal to the concentration of H plus divided by the value for Ka. And so, right, if I look at my value for H plus, I know that's going to be 5.6 times 10 to the power of minus 5 divided by my value for Ka, which we worked out as being 1.66 times 10 to the power of minus 5, right? If I were to put that in my calculator, I end up with the following value, which is going to be 3.37 to 1 itself. And so I can express that as a fraction as well, where I can have 3.37 over 1 itself. So if I were to do the opposite and find the ratio of salt to acid, right, I would do the inverse of everything that I've done over here. And so I would have K at the top, which is going to be 1.66 times 10 to the power of minus 5. And I'll divide by 5.6 times 10 to the power of minus 5. And I end up with the following answer, which is going to be 0.296 to 1. And so if I were to put that as a fraction, what I'd end up with is 0.296 over 1 itself. So yeah, that's how we can work that one out. Now moving on, right, we need to be able to calculate the pH of a buffer solution, but this time using a method 2 calculation itself, right? Now in this example, we're asked to calculate the pH of a buffer made by titrating 50 centimeters cubed of 0.1 mole per decimeter cube solution of ethanoic acid, and our Ka is going to be 1.74 times 10 to the power of minus 5, and then we're actually reacting it with 20 centimeters cubed of 0.1 mole per decimeter cubed of sodium hydroxide. No longer do we have a salt, but instead we've got something, a base, that's going to react with our acid to form a salt itself as well. Now the first thing that I'm going to do is I'm going to write an equation for the reaction between ethanoic acid, which is going to be CH3COOH, reacting with sodium hydroxide, and what we end up forming is our salt. That's going to be sodium ethanoate in this case, and then we end up forming water as well, right? Now the first thing that we need to think about is that our ratio between our acid to our sodium hydroxide is going to be 1 to 1. So ethanoic acid to sodium hydroxide is 1 to 1. So now what we need to be able to do based on this is work out the number of moles of each one, and then find out which one's limiting, and then remove that, and that is going to form our actual salt itself. And normally it is going to be the base. So yeah, let's say if I were to take and find the number of moles of ethanoic acid, CH3COOH, that's going to be equal to concentration times by volume, 0.1 times by 50 over 1,000. I put that in my calculator and I end up with a value of 5 times 10 to the power of minus 3, and that's going to be moles as well. And then I'm going to find the number of moles of my sodium hydroxide in this case, which is going to be equal to concentration times volume again, so 0.1 times by 20 over 1,000 this time, and what I end up with is a value that is going to be 2 times 10 to the power of minus 3 moles itself, right? So I worked out the number of moles of each one, right? I can look at both of these two values over here, and if I were to compare them to my equation that I can see above there, right, I know that I've got a 1-to-1 ratio between the two. So if I were to move this down a bit, if I've got, right, 5 times 10 to the power of minus 3 over here moles of ethanoic acid, 2 times 10 to the power of minus 3 moles of sodium hydroxide. If I were to react, let's say, this sodium hydroxide with the ethanoic acid, I'm now left with 3 times 10 to the power of minus 3 moles of ethanoic acid. And then I'm also left with 0 moles of sodium hydroxide. But if we know that 2 times 10 to the power minus 3 moles of sodium hydroxide reacted, that's the limiting reagent, that's going to form 2 times 10 to the power of minus 3 moles of sodium ethanoate itself, right? So we've actually got now the number of moles for each of our weak acid as well as our conjugate base, as well as our salt itself as well. So I know the number of moles of ethanoic acid is going to be equal to, and then it's going to be equal to 5 times 10 to the power of minus 3, and that's going to be in brackets subtracting, right, 2 times 10 to the power of minus 3, and that leaves us with a value of 3 times 10 to the power of minus 3 moles itself. You do actually get a mark for this bit, and then you need to say the number of moles of your conjugate base, which in this case is going to be CH3COONA, is going to be equal to, and then it's going to be 2 times 10 to the power of minus 3 itself, right? So for this bit here, for these 2 points over here, you get 1 mark for working out the number of moles of each one. And then for these 2 points over here, right, you also get 1 mark as well. And the next step is to find the concentration of H+, which is going to be equal to Ka times by the concentration of ethanoic acid, CH3COOH, and then that's going to be divided by the concentration of our conjugate base, CH3COO minus, and then I really can't be bothered actually working out the concentration, so I'm going to keep it as number of moles. So in that case, I'm going to have, right, 1.74 times 10 to the power of minus 5, my Ka, times by the concentration of my acid itself, which is going to be, right, 3 times 10 to the power of minus 3. Remember, this is the bit a lot of people get wrong. That's why it's good to label your number of moles, and then divide that by the concentration or the number of moles of my actual salt itself. So in that case, right, I know that this in fact is no longer going to be Na, that's going to be ethanoic ions itself, right? So that's something that we can mention, yeah. So in that case, right, what we end up with, right, is the following, which is going to be 2 times 10 to the power of minus 3 itself. I'll put that in my calculator, and what I end up with is the following, which is going to be 2.61 times 10 to the power of minus 5, and that's going to be in terms of mole per decimeter cubed itself. I can then find a value for pH, so pH is going to be equal to the minus log of that, which is going to be the concentration of 2.61 times 10 to the power of minus 5, and what I end up with as my final answer is going to be 4.58 itself, right? So yeah, the next mark comes from your expression, and then calculating the value, and then a value for pH as well. Now I've got an example that I want you to have a go at. Feel free to pause the video and have a go. So yeah, we're asked to calculate the pH of a buffer solution made by titrating 40 centimeters cubed of 0.15 mole per decimeter cubed of methanoic acid. We're told the Ka is going to be equal to 1.8 times 10 to the power of minus 4, and we've got 35 centimeters cubed of 0.1 mole per decimeter cubed of sodium hydroxide. I've got here not a salt, not a conjugate base, but I've actually got here a weak acid reacting with a base itself in this case, so I actually end up with a method 2 buffer. So I know I need to work out the number of moles of each substance first. So the first thing is I need to find the number of moles of methanoic acid, which is going to be equal to concentration times by volume, which is going to be equal to 0.15 times by 40 over 1,000, right? I can do the same thing, right, for sodium hydroxide as well. So I end up with the number of moles of sodium hydroxide being equal to concentration times by volume, which is going to be 0.1 times by 35 over 1,000. And so, right, I put both of these values into my calculator, and I end up with 6 times 10 to the power of minus 3 moles, in this case over here for my acid, and then I end up with 3.5 times 10 to the power of minus 3 moles for my base itself as well, right? So I've now got my two values, right, which I can move to the side. I would normally do it all on one line just to make things easier for yourself, but again, if you can't fit it on, by all means feel free to write a bit smaller. So yeah, there's my two values for the number of moles. Now the next thing I need to do, right, is write out my equation. So in this case, I've got methanoic acid, HCOOH, and that's going to go ahead and that's going to react with sodium hydroxide, again monobasic in both cases. I end up with HCOO, and then it's going to be Na plus, right, in this case it's going to be water itself as well. My ratio again between my acid and my salt and my base is going to be 1 to 1 to 1. So in that case, right, if I've got 6 times 10 to the power of minus 3 lots of this, and I've got 3.5 times 10 to the power of minus 3 lots of this, right, I know that the limiting reagent is going to be sodium hydroxide. All of that will react, and that will actually produce, because we've got a 1 to 1 ratio, 3.5 times 10 to the power of minus 3 lots of sodium methanoate. And so in that case, right, if 3.5 times 10 to the power minus 3 of sodium hydroxide has reacted, we also know that we no longer have 6 times 10 to the power minus 3 lots of methanoic acid. We have 3.5 times 10 to the power minus 3 lots less of methanoic acid. So in that case, we end up with 2.5 times 10 to the power minus 3. And then if I were to express that in terms of a calculation, the number of moles of HCOOH left over is going to be equal to, and then it's going to be 6 times 10 to the power of minus 3. And then we're going to subtract, right, 3.5 times 10 to the power of minus 3. And what we end up with is 2.5 times 10 to the power of minus 3. And that's going to be moles itself as well. So I now need to show the number of moles of sodium methanoate, or in this case, right, our conjugate base. And so I end up with a value of 3.5 times 10 to the power of minus 3 itself, because that's what we formed over here. Remember, that's going to dissociate to form sodium ions and then methanoate ions completely as well. So then if that's the case, I can find the concentration of H plus by saying we've got Ka times by the concentration of our acid itself, which is going to be HCOOH, and that's going to be divided by the concentration of HCOO minus our conjugate base. And so if I sub in my numbers, I end up with, again, I'm going to use the number of moles, I end up with the following, which is going to be 1.8 times 10 to the power of minus 4, and that's going to be times by, right, a value that is going to be 2.5 times 10 to the power of minus 3, and then that's going to be divided by a value of 3.5 times 10 to the power of minus 3 itself, right? So I can plug in these numbers and I end up with a value of 1.29 times 10 to the power of minus 4, and again that's going to be in mole per decimeter cubed, and then I'm going to find pH, which is going to be equal to minus log of that value. And so I end up with the value of 3.89 itself, right? So there's our final answer. So moving on, I've got an example here that's a bit more trickier for you to try. Feel free to pause the video and have a go. So yeah, we're told a student plans to make a buffer solution of pH 4 from a mixture of ethanoic acid and sodium ethanoate itself. We're told that the student mixes 400 centimeters cubed of 0.204 mole per decimeter cubed of ethanoic acid, and that's going to be with 600 centimeters cubed of sodium ethanoate solution. And we're asked to calculate the concentration of sodium ethanoate needed to actually prepare this buffer solution of pH of 4, right? We're told a value for Ka that we can use over here as well, and so, right, we actually need to work backwards in this tricky calculation where we need to find the concentration of H plus, then we need to find the actual concentration of our acid, and then we need to find our concentration of our sodium ethanoate itself, and then we also need to be able to think about what type of buffer calculation we've got, which in this case is going to be method 1 itself, right? Because remember, we've got a salt and we've got an acid mixed together to form a buffer solution, right? So the first thing I'm going to do is find the concentration of H plus, which is going to be equal to, right, 10 to the minus pH, which in this case pH is given to us as being minus 4 itself. So pH is 4, I'm going to do minus 4 to get the actual concentration, and so I end up with a value that's going to be 1 times 10 to the power of minus 4, and that's going to be moles per decimeter cubed itself. So to start off, right, I'm going to write an expression for the acid dissociation constant, which is going to be equal to concentration of H plus times by the concentration of our ethanoate ions, which is the same as the concentration of our sodium ethanoate. And so in that case, we end up with ethanoate over here, and that's going to be divided by the concentration of our acid CH3COOH itself. And then what I need to be able to do is actually rearrange this to make the concentration of my conjugate base of subject, which is going to be CH3COO minus itself. And to do that, right, I'm going to take this over here, times both sides by my concentration of my acid, and then I'm going to divide both sides by the concentration of H plus to get that on its own as well. So in that case, right, I end up with the Ka value times by the concentration of my actual acid itself, and then I'm going to divide by the concentration of H plus, which I've actually got in this case. So again, in that case, right, I'm going to sub in my numbers, and so I end up with 1.78 times 10 to the power of minus 5, and then I'm going to times that, right, by the concentration of my actual acid itself, which I need to calculate, right, by taking 400 centimeters cubed and the concentration as well. So I'm going to do N of ethanoic acid is going to be equal to concentration times volume, which is equal to 0.204 times by 400 over 1,000. And so I end up with a value that is going to be 8.16 times 10 to the power of minus 2, and that's going to be in moles. So I find the number of moles, and then I can find the actual concentration of that, right, by taking, right, the actual number of moles that I've just calculated, which is going to be CH3COOH, right, is equal to the number of moles divided by the volume, and so that's going to be 8.16 times 10 to the power of minus 2 divided by the value of the volume, which in this case, right, is going to be 600 added to 400, and so what we actually end up with is 1, and so our value for the actual concentration is also going to be 8.16 times 10 to the power of minus 2. Remember, you've got 1,000 centimeters cubed in 1 decimeter cubed itself. So yeah, there's my concentration as well that I've just calculated. Now, if that's the case, right, I can plug in my values, and so what I end up with is over here in this bracket over here, 8.16 times 10 to the power of minus 2, and then I'm going to divide everything by the concentration of H plus, which is 1 times 10 to the power of minus 4 itself. Now moving out of space here, so I'm going to move that to the left a bit. Now I end up with an actual value for the concentration of A minus, or our conjugate base, or our salt, which in this case is going to be sodium ethanoate, as being 0.0145, and that's going to be mole per decimeter cubed as well. Right, I've got my concentration there. Now I need to find the number of moles, right, and then find the concentration in 600 centimeters cubed, because this value here is a concentration in 1 decimeter cubed. So in that case, the number of moles of sodium ethanoate is going to be equal to the concentration times volume, which is 0.0145 times by 1. That's going to be the same number for the number of moles. And then I'm going to find the concentration of sodium ethanoate by doing the following, where I take the number of moles divided by the volume. That's going to be 0.0145, and the volume here is going to be 600 centimeters cubed. So that's 600 divided by 1,000, and what I end up with as a final answer is going to be 2.42 times 10 to the power of minus 2, and that's going to be in mole per decimeter cubed itself. So there is the concentration of our original solution. So moving on, right, sometimes you could actually be asked to explain how a buffer solution is actually formed. So let's say in this question over here, we're asked to explain using equations how a buffer solution forms when excess propanoic acid is mixed with sodium hydroxide, and how the buffer actually controls pH when an acid or alkali is added as well. Now this can come in form of a 6 marker, and straight away you can see over here, right, propanoic acid mixed with sodium hydroxide. We've got a strong base, right, mixed with excess weak acid. That's going to be method 2 straight away, right? We're not dealing with the salt. We make the salt within the actual beaker itself. And if we were to look at the preparation of a buffer, we need to say the following: that excess propanoic acid is going to react with the sodium hydroxide and is partially neutralized. We need to say that some acid actually remains and propanoic ions are formed itself. Now always talk about the acid that you're dealing with, the base that you're dealing with, and what conjugate base that you're actually going to form as well. Give an equation for the reaction, make sure it balances as well, and once you've done that, you can make a buffer equation, which is where you have your excess weak acid and then you have your conjugate base and H plus there as well. Then you need to talk about what happens when you add acid. Well, when you add acid, right, what's going to happen? The ethanoate ions itself is going to react with the added H plus, and so it's going to shift the equilibrium to the left. And then if you were to add in alkali, the OH minus ions, they're going to react with the actual acid itself right over here, and that's going to shift the equilibrium to the right itself to make more of this substance over here. Yeah, and so in that case we can say that any change in pH is going to be minimized.